John? Okay. I'm Rob Napier. This is Secrets and Lies. In 1942, the U.S. Marines enlisted 29 Navajo speakers to send secure messages over the radio. Eventually, there were 421 of them serving through World War II, the Korean War, and part of the Vietnam War. Their secret code was little more than speaking Navajo, plus this ingenious encryption scheme for spelling things. Genius. No one could break that. Except they couldn't. Why Navajo? Because frankly, nobody knew Navajo. Outside the Navajo Nation, they thought maybe there were about 30 people who knew the language, right? And it has a complicated grammar, it has very unusual sounds, and there wasn't a writing system until nearly 1940. So there were no books that you could use. And Navajo isn't special here. There were also some other tribes, the Hopis, the Cherokees, there were several other native tribes who did this. It was very effective. This is the ultimate in security through obscurity. Also, 1942. The pinnacle of German cryptography is the Enigma machine. It had been around for about 20 years at this point, and it had been iterated numerous times, improved over and over and over again. And it is definitely what we call security by design. There is really just one secret in the Enigma machine, a key that might be encoded in numerous ways. There are plug boards and rotors and everything else, but they basically come out to a complicated way to say a password, and everything else about the machine could be known. They didn't tell everybody, of course, but you could know. That was not the point. The point was the key. This is what we call security by design. Okay? So we have the ultimate in security by obscurity against the best security by design of the day. How'd they turn out? Well, through 3 wars, we do not believe that a single message from the Navajo code talkers was deciphered. Throughout World War II, if you've been watching the movies and everything else, you're probably aware, we broke, except for the Navy's codes, we broke Enigma codes pretty regularly. So security through obscurity, that's what we're going to be talking about today. Before I came to iOS, I was in information security. That's what I used to do. I did audits, I did assessments, I used to sneak into buildings and talk my way past guards, I did physical security, I did all kinds of stuff. My big thing was anti-counterfeiting of equipment. Everybody always assumes I mean money, but of networking gear. And as every good security, highly trained and certified security professional will tell you, there's this thing called Kirchhoff's principle, first published in 1883. And what he said, in French, but this is the English, we usually boil down to a crypto system should be secure even if everything about the system, except for the key, is public knowledge. I was like Shannon's maxim, which tries to sum it up as the enemy knows the system. Or, as we typically tell everybody, security through obscurity is no security. Another story. Alfred Charles Hobbs, at the Great Exhibition of 1851 in London, he demonstrated how to pick some of the most advanced locks of the day. He was questioned about this. He was like, is that a really good idea to show all the thieves how you pick the best locks, the ones that are guarding many of the royal jewels and everything else? He actually picked some of the locks that were, in fact, protecting the royal jewels. He had a response to that. Rogues are very keen in their profession and know already much more than we can teach them. This continues to be true today. Most door locks, pointless. No point. They can be picked in less than 30 seconds. Go to YouTube. Google for lockpick deadbolt. You can watch people do this all day long, right? And that's by hand. There are pick guns, there are bump keys. I've seen locks picked in 2 seconds. Lock manufacturers know that. You can, in fact, spend extra and get locks that are difficult to pick, or more difficult. But most locks you get every day, they're pretty much pointless. I mean, they can be picked almost immediately. Another thing, a lot of institutions have this thing called a master key system, where you have like a master key that opens most of the doors and regular keys that can only open one door. In 2003, Matt Blaze publishes this great paper where he works out how you can take a regular key and upgrade it to a master key. And it doesn't take a lot of skill. It doesn't take a lot of equipment. It's a pretty easy attack. And that's not surprising. I mean, people find vulnerabilities all the time. But the locksmiths were not pleased. They were furious because they said, we've known this for a century. Why are you telling people? I was like, this thing has been known for 100 years by locksmiths and lockmakers and thieves, but not by the people who buy locks. But fixing it makes locks a lot more complicated, makes them more expensive. They didn't want to fix it, and locksmiths also use this fact to open doors. That's why you can call up a locksmith and they can come and open your door. So, we come back to this. Security through obscurity is no security. But this is a lie. It's at least not completely truthful. There's a big difference between these two stories. Big difference. The Marines were using obscurity as a tool. The US government had crypto systems, had good ciphers in World War II. Why did they get Navajo code talkers? The reason is because it's really slow to encrypt in the field when you have a message to send. The crypto systems took a long time to encode things. They're very complicated. You could hand it to a Navajo speaker, they could translate it in their head. It was fast. They were optimizing for something other than ideal security. They recognized that it was less secure, but that was worth it to get the message out fast. This is completely different than the lock story. The lock story is we just hope nobody notices, right? Very different things. One is being used as a tool, the other is being used as a cop-out. So let's talk about the tool. I want to talk about the tool of obfuscation and obscurity, right? It's not as powerful as cryptography. Cryptography is much more powerful, but it doesn't mean it doesn't have a place. So today we're going to take a trip through the badlands of security, to the disparaged and the discredited, and we're going to talk about obfuscation. So I keep using obscurity, obfuscation, I keep treating them like the same thing. They're not. They mean different things. Obscurity means you just don't tell anybody. And by the way, it's always pretty good. I mean, even no matter how secure you make your system, there are certain advantages to just not telling everybody. There's advantages to telling people too. Obfuscation, on the other hand, is the act of trying to make it hard to figure out the system. And that is a different technique. But they're both different than cryptography. So in cryptography, there's some secret here that is outside the system. It's often stored in a person's brain as password, but it might be stored other places, an RSA key, or lots of places. There's HSMs, there's lots of places this might be stored, but it's not in the system. In obscurity or obfuscation, it's in there and you just hope nobody goes and finds it, right? The key is in the system. So as app developers, what this means is if you can decrypt something without the user's help, it is probably not encrypted. There's in fact a technical term we call it scrambled, right? Just to distinguish it from encrypted. Now, cryptography makes strong, provable claims. It is much more a math than a piece of computer science. And it typically is based on highly technical definitions of what it means to be secure that have little in common with what most of us think of as secure. This comes out of my notes when I was taking classes in cryptography, and this is the kind of thing that cryptographers will draw up and go, this is what a proof means. I'm able to play this game that has to do with whether or not the adversary can determine whether I'm using a cipher or not, right? If they can even tell that you're encrypting, you failed. Well, that's usually not what most of us mean. Most of us mean, can they get the data out? Cryptographers typically, if you've gotten all the way to actually decrypting things, cryptographers are uninterested. They were worried way, way back where you could even figure out what the structure of the data was. But these, as strong as they are, and as mathematically provable as they are, is not how security works. There are other ways to get keys. Some algorithms that fail all of that test I gave before, that's the pseudo-random permutation test, might still be adequate to your purposes. What really separates security from obscurity is in cryptography, if you lose your key, other people who are using AES or RSA or the like have no problem. It doesn't affect them. If your obfuscation technique is worked out, then everybody else is using the same technique, or especially a obscurity technique, if you're just hiding things. Then everybody else is using the same scheme is in trouble. That's the difference. Practical security is risk management. A common way we talk about it is raising the bar. I actually hate this. I almost always know when I hear somebody say raising the bar, they're about to say something, let's say, foolish. It's great advice, it is true, but it's not always that helpful. I want you to think in terms of a 3-inch fence. You've built a 3-inch fence on your grass, you don't want anybody to walk across it. That will stop some people, right? It is actually an effective security deterrent. It is honestly effective. A sign might be effective. Keep off the grass. This is not useless. This means something. It can work. But if you already had a 3-inch fence and you go to a 6-inch fence, that's nothing. It's literally nothing. You just wasted money. There is no big group of people who would have gone over a 3-inch fence and won't go over a 6-inch fence. There's no joke. I don't have to be faster than the bear. I just have to be faster than you. A lot of things about security are, or of what we're going to be talking about today, are how do I just make it hard enough that you'll go somewhere else? I was saying that this is the continuation of Derek's talk. And for this talk, I want you to understand Derek is a very nice person, but he's the enemy. And we will be trying to defeat him. Now, we will not defeat him, but we will try to make his life just that much harder so he will go somewhere else. Because we're not that interesting, please don't look at us. He will beat us if he tries. Nothing I'm going to tell you will stop that. But at least I can make him, maybe I can make some of his scripts not work, for Pete's sakes. I don't want you to be thinking in terms of, I want to make it twice as hard. I want you to be thinking, I need to make it 10 times hard, 100 times hard, 1,000 times harder. If it's twice as hard, it doesn't matter. We are mostly going to be fighting bots, scripts, things that are dumb. Every app on the App Store we know is downloaded by various folks who jailbreak it immediately, automatically, and scan it. Or crack it and scan it. We know this because white hats do it. If white hats do it, I assure you black hats do it. And they look for things. Passwords, API tokens, just see what it has, automatically. And they're equivalent of walking down the hall trying doors. And I told you the door locks are kind of useless, except maybe they get the guy to go on to the next door. Let's look at the easiest tools. These are the most basic things. This is my favorite one, is the first one I always use, is strings. Just give me the strings. Tell me what's in this thing. You can take your IPA, dig down into it, run strings against it. And I usually like to add N8 to say I only want things that are 8 characters or longer. The default is 4. You get too much garbage. This still generates a lot of garbage. I mean, it'll be hundreds of strings, even for the most simple app. But it's not that hard to write a little Python script that will fix all that and get you down to some things that look interesting. Interesting things like URLs. That's a password. You know it's a password. The next one, that's probably some kind of API key, probably to Amazon. It's 20 characters long. That's what they look like. The last one, that's base64 data. That's probably interesting. Maybe I should tear all this stuff into a database and look at it later. When I'm trying to find an S3 key so that I can store this, I have some stuff I'd like to store it. I'd like to bill you. Maybe I have a key sitting in my database. So what do they use? We're going to go a little beyond strings. This is Hopper. Hopper is my favorite tool because it's $100 and it does a pretty good job. There are better tools, but they cost thousands of dollars, and I defend systems I don't attack. So I don't need the thousands of dollars. But for $100, you buy Hopper. It's a little nicer than doing all this in LLDB. And it'll give you this. Pops up, you get all the symbols. Go in, you get all the strings. You get this, not just assembly language, but there's lots of places where they put in comments and say, oh, look, this is the beginning of this function, and here's where everything is to help you find your way around. It can give you some structure. I want you to understand what kind of tools people are looking at your code with. They can see the structure of like how things flow through, and you can create this kind of crazy pseudo-Objective-C decompiler. This is where the big money is when you buy big expensive tools. It does this part better. But you can just look at this, and you see there's an URL request right there. This is probably doing an URL. I mean, you can already start to see the structure and the types. This is effective, especially against Objective-C. I want to be very clear. Objective-C is a reverse engineer's dream language. I don't want you to think that Swift is really super hard to reverse engineer it. It's not, but it's nothing like Objective-C. Because Objective-C is filled with strings that you can't get rid of, and names you can't get rid of, right? But that means everything you do in Swift that touches Objective-C in any way, including you subclass for it as an object, or you are calling a Cocoa method, or you're touching anything using the Objective-C runtime, all of that will tend to make your Swift look like Objective-C. The biggest problem, in my opinion, with Objective-C, if you're trying to hide anything, is it is very hard to optimize. And you'll have all kinds of people try to sell you expensive products to do obfuscation. If you want to have the best obfuscator I've ever encountered, try an optimizing compiler. Aggressive optimization makes code a nightmare to read. So things that you do to help it be optimized absolutely are great for making it hard to reverse engineer. Okay, so I show you a lot of stuff, who might attack you or whatever, but I'm just like, okay, fine. But what do I do? What do I actually do? Okay, the first thing we should be doing is get the secrets out entirely. Don't solve engineering problems, make engineering problems go away. How do you do it? Fewer secrets. So it's like, how do I store all these sensitive API keys in my app? Don't. Your first question should be, how do I get them out? Right? Can I download them from the server? Should the app have it at all? Can the app, for instance, I always advocate strongly, proxy, if you use third-party services, say you're using S3, or you're using Google Maps, don't talk to it. Talk to your server. Let your server talk to it. It gives you so much more power. It lets you change your backend. I mean, it has great operational advantages. It lets you change your keys. It lets you fix things up, but most importantly, it allows you to watch what's going on, detect that that you're being attacked, and control it. And also control the kinds of requests you accept. If you allow your app to talk directly to Google Maps, or to S3 is a great example, if you allow it to talk directly, you have to worry about every possible thing the app has the power to do. But if it only talks to your server, and your server talks to S3, you can say, well, there's certain things my API doesn't allow. That's why I always recommend going through that way. When possible, you want to have users. It is hard to authenticate an app. It is actually flat out impossible. You cannot authenticate apps. You cannot authenticate devices. You absolutely cannot answer questions like, is this device jailbroken? I want you to think about that for a second. It's the number one question I get asked. How do I tell if the device is jailbroken? Well, you would use the technique that Apple uses to determine if it's jailbroken. And of course, if they had that technique, it wouldn't be jailbroken. Right? What do you think you're going to do in a sandbox app that Apple couldn't have done? And that you're going to come up with in a weekend? That they couldn't come up with a team devoted just to that problem larger than your entire development organization. Instead, move the secrets into people's heads. Authenticate your users, give them accounts. I know it's not always possible, but that's the direction you want to be moving. You can go the other way too. A thing called honey tokens. Actually put things in your app to be found. Authentication tokens, URLs, that aren't used. And then you monitor them. When someone shows up with this credential, you go, wait, somebody is attacking my app. Clearly the only place that they found this was by digging through my app. Or the fact that they came across this URL that isn't linked anywhere, but is in my app, somebody's attacking you. Then you know. And also when you don't see any of those, you're probably not being attacked a lot. It should set how much effort you should be putting on these things. One thing about that, you want to make them global variables. In Swift, right now, global variables are never optimized away, even if you don't use them. But watch that space, they may someday start doing that. You have to look, make sure that they stay in your app. But if nothing else, the biggest thing is you have to pay attention. I keep talking about, and you check your server logs, and you monitor. And if you're not doing those things, if you have a safe somewhere and you put all your precious things in it, and then you never look at it again for 50 years, I don't know if it's still going to be there or not. I'd rather go and check from time to time, make sure that things are that you're not having problems. That means paying attention. Okay, I keep dodging and dodging and dodging, and what we said we were going to talk about is actually hiding stuff. So let's actually hide some stuff. Let's not just get it out. Sometimes you do have things you need to put in your app. So let's say we got this thing. We got some key, it's base64 encoded, and we want to hide it. The first thing is, you should never have data that was sensitive and put in base64. Base64 moves it into the string space. And as if you've watched mine and Derek's, you've seen the first place we all go is the string space. It's the best place ever. You don't want to be in the string space. Why would you take random data? All base64 is an encoding of arbitrary data. If you had arbitrary data, why would you encode it? You already had it. Turn it into data. Let it be itself. Since you already have that probably, and you don't know what the data is, you can go to the command line and ask with base64.d and say, please decode this back to real data, and then pass it to my favorite little tool, xxd, with -i, which says, please make me an include file for this. What it does is it outputs this. And what's so wonderful, this is C code. It turns out C code and Swift codes are identical, and therefore you can just copy and paste this directly into your data. That's why I like xxd-i so much. Now the problem is, it's like, yes, yay, that's better, that's way better. But it moves into the data section, good, better than strings, but it looks like this. 0, 0, 0, 0, 0, 0, 0, 0, 0. Oh, look at all that, 0, 0, 0, 0. That's the problem. And it's exactly 32 bytes long, and I tell you, to all of us who do representation 32 bytes long, that's an AES56 key, I promise you. It's the only thing that, it's exactly 32 bytes long. It's the only thing that is. So we go, oh, there it is. And it's word aligned. It's right at a boundary. Yeah, okay. So I know, okay, we'll get back to this. Put that to the side. We'll figure out better things to do. But this idea of getting it out of strings and into data, it's the first step. No strings, no strings. Well, if it really is here it is a string, right? So if you just encode this as data, it doesn't actually buy you much because the strings executable, as I recall, doesn't check the string space, it checks the whole binary. So we'll actually find it anyway. Even if it's data, because it's just looking for the ASCII code. But again, that is a 32-character password. That means it is a lousy, lousy AES key. No AES key should ever be typable in letters. AES keys need to be random bytes. So how do I make random bytes? Random gives you random bytes. You can take the first 32 bytes out of that random, and again, xxd. That's a great way to just generate random things. Don't try to guess things. Don't try to make up things. When things should be random, ask for random things. And this will make your key incredibly stronger, wildly stronger, 100 trillion times stronger. That's not a made-up number. 100 trillion times. That's how many more 32 byte sequences there are than 32 typable character sequences. 100 trillion times. Why? Because there's about 96 symbols you can use that you can easily type on a keyboard. And I'm talking about you're just typing totally randomly every possible key. I mean, every shift, all of it, you're doing it totally randomly. You didn't make up anything. So it's the best possible one you could ever do. When you compare that to the number of 250 full bytes, it's a tiny space. All of the power of cryptography comes from the fact that the key spaces are enormous. So don't shrink them. Okay, what about this one? This is an access token, and I can't get rid of it because that's what it is. I mean, I can't make it random because that's what it is. I mean, and they're letters, and what are you going to do? I told you, get it out of your app, but maybe you can't. What do we do? So now we're actually going to do real obfuscation. We're actually going to, let's scramble something. I encourage you to make up silly ways to scramble things rather than come up with universal ways to scramble things. Because remember, the whole point was that nobody knows how you did it. That's the only thing you have going for you. So when you go out and find something on GitHub, I promise you, if you found it, the attackers found it. You want your own made-up thing. I'm going to show you some tools you can use to start making up things. I have this thing called Swift Mask that just a little tool so you don't have to remember all of these little things. I'll show you the URL at the end. But it'll just write a little bit of Swift code that does one particular scramble, which is get 20 bytes of this. It was a 20-byte string, so 20 bytes. It's the same number of bytes as the thing you were trying to mask. Totally random. So now I have a mask. Now I'm going to zip it up with the API key. All right? With a little hat. That's XOR. So XOR is the only operation that cryptographers know. They can't now multiply. They don't know anything. They know how to XOR. And that's what you're typically going to do. That generates more random data. Now you have a mask that is totally random nonsense, and you have masked the other half of it that's totally random nonsense. These have no structure to them. It's actually provable that this has no structure. This is technically the best crypto that exists. It is provably secure. It's called a one-time path. We're then going to destroy the security by putting the key in the source code. But if you didn't do that, this would be the best key ever. It is provably unbreakable. So there I have these two things. And the nice thing is I just also created 2 honey tokens. Neither of those should ever leave the app, right? Because they're both nonsense. So if either of those things ever show up at our API, we know somebody's messing with us. And then to do it, it's just the other way around. You just zip them again. You put them back together and out pops the original answer. That's the great thing about XOR. This works just as well, by the way, with data as much as strings. I kind of showed it with strings. Perfectly good with raw data. So if we think about that thing we were talking about before, where I have this blob, I could do that again. I could take that key and split it into 2 keys that were each 32 bits, or 32 bytes long, and maybe try to spread them around a little bit. Which is good. It's a good technique. I'm not going to show it because it's the same thing. But it still kind of creates these 32-bit things, or 32-byte things. And the thing is, my scanning tools look for 32-byte sequences and spit them out. So you've told me there's something I want to go look at. I want you to not think there's any. I want to hide the fact that there's even something to look at. So what can I do? This comes from a line of code that looks like this. That's what's going to happen. It's going to show up in your data section. So what can I do? I can just come up with some more bytes. I'm going to pick 20 for no particular reason. I picked a random number of bytes, and I'm just going to generate a couple and stick them at the top and the bottom. These are different. They both are 84, but they are in fact different sequences. In fact, I wanted to change it because it's like, oh, 84. It looks like it's the same sequence. Don't feel the need to tweak random numbers. Random numbers are random, and sometimes they have patterns. That's normal. So many crypto systems have been broken because people went in to try to make truly random things look random and break the whole crypto system. So anyway, you do that, and then you just slice out the middle. So now I have a thing that doesn't look like AES-256. I have this big blob, and I have some random offset into it. Again, I'm just trying to drive Derek crazy. That's all I'm trying to do. He's going to break it, because he's just going to debug the whole thing, find when you undo it, and then he pulls out the key, right? You're not going to win, but I want to force people to use a debugger. I want them to waste an hour messing with it. There we go. This is part of a bigger study. It's called steganography. Steganography is the attempt to hide things. As opposed to encrypt things to make them unreadable, I want to hide the fact that it exists at all. I just want them to move on. So one type of steganography, I'm not recommending this, I'm just trying to explain how things might work. I might have in my bundle the MIT license, which is quite a natural thing to do. I mean, it's a mistake, but sometimes they wind up, you usually should put license text into your bundle. I guess if you're going to show it. But what I've done is I've gone into this file, and everywhere there's a space, I've actually used the Unicode N space, or M space, to encode binary. This is what stego looks like. The goal here is you don't even know I'm here. This is the thing that I'm thinking very hard about right now and trying to build tools that don't leave fingerprints. I think I put it down here. There's not much there yet, but watch that space. I'm hoping eventually to have things. That said, I want to be clear. I am overthinking this part because that's my background. That's my passion. Don't overthink this stuff. You will screw it up and you will make it worse. There are a lot of things you can do. Stego can make things worse. And a lot of these kind of things, if you make them really complicated, you start leaving fingerprints that you didn't. I have dealt with so many people who've created secure string libraries and put them on GitHub. And I pulled them down, I'm like, I try running them, and sure enough, as soon as I pulled them up, what you just did is you put a laser pointer on every string you consider important. And they're easy to reverse engineer. They're super easy. And you told me which ones you cared about. So now I can write a tool that just says, do they use that? Tell me all those strings. I just want those strings. So don't do that. Keep it simple. Okay, let's move on. New topic. Scanning for strings is so easy that you should expect it to be done. If you have a plain text string in your data, it's gone. That said, you can move up a step from that and watch network traffic. And network traffic, it's a little harder to automate that. I mean, it's possible, but it's harder. So people still may do it to you. So what do you do? What does it mean what would it look like? This is a tool called Charles that I happen to like. It's like $50. And this little app I built that just sends something over HTTPS. And sure enough, I see it popped up, but I see the host, but I don't see a path. I have no idea the rest of the URL. All I know is the host it went to, and the data itself is completely unintelligible. So that's working. I mean, SSL is working. SSL is doing its job. It should be SEA. But I can go in, and while this is tested with a simulator, just because it was easier to do a screenshot of it, this works on devices just as easily. I'm going to install some special routes. This is not hacking the device. This is totally supported by Apple, 100%. This is a feature. This is not a bug. And install it, and we have to relaunch it because the simulator doesn't always capture it. But now I'm going to send again. First I have to go in and say, hey, I want to enable SSL proxying. And let's HTTPS, secret, secure, totally readable. Now, why does that work? Again, this is working because you're trusting, my app there is trusting the certificates that are in the root store. Why are you trusting the ones in the root store? You can fix this with a technique called certificate pinning. I'm not going to go fully into this. I'm going to skim through this because I gave a talk on this last year, and I have a whole other talk just on this, 20-minute talk on just this problem. So we're just going to breeze through it because I want you to understand how it's used. The main thing is there is a lot of trust in the current keychain. iOS 11 has 170 root certificates. You probably need one of them, maybe two, of the providers you actually use. One of them, for instance, I helped put in there, the one from Cisco there. I actually helped put that one in there. I promise you, you don't need to trust it. Because Cisco is never ever going to issue you a cert. So you don't need to. What you want to do instead is say, I have a certain group of certs. Maybe even every cert that Apple trusts, I trust, but I'm not going to trust random certs that the user stuck in here, right? Don't copy. So this is what it looks like. This is kind of obnoxious. It's like a page of code. It's all this nasty, nasty C API. So I rewrote it and made a little bundle for it, right? Certificate validator. If you don't want to use that code, it still is a great place to just see how do you do it yourself. I mean, it's like one page of code, and it's not that hard to understand. But I recommend to everybody to pin certificates. It's not just good for you. It's not just for making sure people don't watch your traffic. It is also good for your user because if any of those 170 certificates are compromised, your users may be compromised. By pinning to smaller sets, you're protecting them. So even if you didn't have sensitive data, I still tell people, pin your certs. Okay. What else? I'm dealing with a network service. I like this script. These things are silly, but surprisingly effective. A secret knock is just an API key that you've hard-coded into your app. I told you don't hard-code stuff into your app. Okay, but this one, we're going to hard-code into the app. And we'll probably use obfuscation techniques to try to hide it a little bit. And we use Charles so that you don't see it on the wire. It's hard to see. And it just means that when folks come up and they just try to attack your API, they're just trying to probe your API, right? It's hard to talk to you because they don't know your API key until they know it. So what do? We generate a secret. I mean, the simplest form of this is really simple. Generate a secret, which is just cat from dad random, and spew it out, maybe base 64 encode it because that's easier, to put into your header or into the URL or however you like to do your API keys. This is just in addition to all the other ones, right? User authentication or anything else. It's just, you have to have this one, or I don't even talk to you. And in fact, if you don't show up with it, I don't return you a 400. I don't send you a 401. I send you a 404. Nobody's home, right? Don't even let them figure out which endpoints exist and don't exist. If they don't have the API key, go away. I don't know, send them 500, I don't know. And it helps. Like I say, people go, but that doesn't really help. I mean, why does just messing with your protocol help you that much? Similar form is, it's ridiculous to encrypt with AES before sending it over HTTPS. Why do double time? True story. So I got this contract. I do crypto systems. I build cryptographic things for people. And these folks came to me. They actually had one in Android that connects this. It's actually a very secure setup. They did a great job with it. I loved it. But they were talking in Android, and every connection, you would come in and you would get an encryption key, and then they would, all of the messages back and forth had to be encrypted with the encryption key. There was an upstream and a downstream and everything else. Now it was just obfuscation. You could get the key, right? Because you have the session. But it was all encrypted there. But if you didn't do the right thing, it didn't even send you an error. It would send you garbage that when you tried to decrypt it, it didn't work. I mean, it looked fine until you tried to decrypt it. Well, now you don't know, is it my encryption, my decryption? Am I sending the request incorrectly? What is it? I had a fully working copy in Android, right? I have full thing to do it. It took me most of a week to implement this thing, and I was doing it, they're paying me to do it. And I'm pretty good at this. And it took me about 20 hours of work to figure out this protocol. Hopefully in 20 hours, and probably quite a bit more, if you didn't have a working implementation right here to work with full source code, maybe it'll go away, leave you alone. So these kinds of things, that's the effectiveness. So what if an attacker is going to spend more time in your app? They're actually, they're going to do more than basics. They've got IDA Pro, they're going to run it on a device with a debugger, they're going to tear it apart, right? And they're just going to print out the keys, after they find where you finished decrypting, and then they just print out the key. And what do? I'll say for almost everybody in the room, the answer is nothing. You've lost, move on. Accept it. You're not going to win. And the amount of money and effort and time that you try to put into stopping it is poorly spent. Now, for some groups, your business actually does rely on it, and in which case you need to hire a team who does this professionally, right? Because you have a serious problem. But if you're just trying to make the bots go away, you're not going to make a more advanced attacker who's coming after you. You're not going to stop them. You're going to slow them down by maybe an hour or two, frankly, at all. It's just the way it is. But what I do recommend you do is you try attacking your own system a little bit. Figure it out. Spend a few hours. Pretend you're the attacker. What do? Build it up and open your own app in Hopper. Check it out in Charles. It's about $150 investment. There are cheaper tools, but those work really well. Build it to do Hopper, you don't want to be running it in Xcode. You want to see what it looks like from the outside. So you're going to make a full archive, and you're going to run on the simulator. But Hopper can't debug on the device. That's one of the things you get when you pay thousands of dollars rather than hundreds of dollars. So you can debug in the simulator just to see things. But you want it to be kind of real. You want it to be in a release mode, etc. You want it to be optimized. You want it to be what it would really look like. And so you need to launch it without xcode. How we do that? Well, you need to attach this other debugger hopper to it. How do you do that? This took me forever, that's why I'm sharing it with you, because I couldn't figure out myself for hours. But you can use sim control, and you can say launch. Booted just means the currently booted simulator, right? Your bundle, whatever your app bundle is. And you say the special thing though is wait for debugger. It just says launch and then hang out until the debugger comes along, and then proceed. That way you can start debugging from the very, very beginning, which is really important because a lot of things that are really interesting happen in things like application did finish launching. So you want to be attaching at that point. The other pieces, though, are attached. You want to be periodically sniffing your own traffic with Charles or with other types of things, Wireshark or whatever you like, because you want to see, is my pinning working? Am I leaking things? Am I connected to weird services? I do this quite a bit to find out that some framework that I've imported is doing analytics that I did not approve. And that makes me have tense conversations with their developers. What about if we go even further? What if we have obfuscation tools, that you pay for? Or just obfuscation tools generally that do things like rename everything and mess with things. The thing is, it's really hard to do renaming in a way that is meaningful. Most of these things that try to scramble your code, it's not worth it. There are some, and we'll talk about it in a second, but you can't change most of the names in your product because you talk to Coco. And the truth is, the names of things aren't really the important thing in reverse engineering. I've taken out all of the user-defined names here. I've named them A, B, C, D, E, F, G. I'm sure no one here can figure out what this does. This is a mystery. You're totally baffled. What do those functions do? Okay, in fairness, this isn't quite what it looked like. If it was truly obfuscated, it would look like this. Which, that's a little harder, right? It's a little harder. Except that this isn't what it looks like in Hopper. This isn't really true, but once you understand how to read Hopper output, this is what it looks like. You get all the types. You can't hide those. They're necessary at runtime. And again, I'll come back to you. It's like, I wonder what function takes a closure with data or response and error. It's like we all know what this is doing. And then you can start going in here and you go, oh, I know what that one does. I know what that one does. I start renaming things. I clearly know that that function is that. And again, in most of these tools, you can go in and say, once you figure something out, you just rename it, and it fixes it through the entire code base. And from then on, you know. So they can reverse engineer your whole thing and get it back basically to, how far? Up to this. You could get it to. So that's not very good. And that's frankly, with pure renaming, I found this in every language I've talked to, when I talk to people in PHP and JavaScript and Java and everything. It doesn't help, right? It doesn't really help. There is such a thing as hardening rather than obfuscation. Hardening is all about actually making it hard to stick debuggers on things. There are ways to detect that a debugger is currently running and trying to stop that. There are various things you can do to bloat the code, to create dead ends that go nowhere, to make the code insanely inefficient. But it's very, very expensive. It's very, very bad. It's hard to develop with. I don't recommend it. But if you're going to go down that road, expect to spend a lot of money. Security is a logarithmic function. You will spend a lot of money to get a little bit of improvement once you get past the very basic. And my goal is to get you from this terrible point to basic. I just want to get you there. This talk is really about this outcast of security. It's obfuscation. There's a reason it's an outcast. It's not nearly as powerful. It does have these uses. You just need to remember, it is for you. It is not for your users. Nothing about your users' data should ever be protected with obfuscation. Only cryptography. Because obfuscation is not strong enough to protect a user's personal information or private information, right? No business with that. Focus on the basics. Get things out of the strings. Focus on the network. Make sure the network's not sniffable. Basic tools. Hopper, Charles. Strings bad. fatal less bad. Objective-C is so bad if you want to hide anything. I still love Objective-C. Don't talk bad about it. And that's it. I might have a minute for questions.
Are there any methods for securely getting API keys, something like that, into teaching and deploying that as part of app deployment so that, the App Store is doing this in a secure process? Or
Well, it wouldn't change anything. That wouldn't help you very much.
You don't think so? Like, if it's a one-time do it install, we're not at that point yet.
Well, you can't. I mean, you can't put things in there without your code running, so the App Store can't do it anyway.
Right.
But the keychain's not particularly any. I mean, it is a better place to put secrets for the user's secrets, but it doesn't particularly help for your secrets. I mean, it's totally readable by the user. So, yes.
So what are your thoughts on jailbreak detection and disabling functionality?
So jailbreak detection, as I was saying before, if there were a way to reliably detect jailbreak, then Apple would just use that to brick the device. But that's not to say that it can't be done at all. There are techniques. I mean, there are certain things that show up in certain particular jailbreaks lead to certain artifacts that can be detected. I would always start with just sending yourself messages. Again, I like monitoring and incident response more than trying to proactively do things. Because I promise you, you will inject bugs and you will impact paying users when you meant not to, because it's the kind of stuff that's really hard to test. How are you going to do your unit testing of that code? How is even your QA? Does your QA have a stack of jailbroken devices that you're going to use to test this all the time and maintain it all the right? And when you start putting code into your app that is not tested and is not usually used, that is where bugs happen. So I don't like it. It's the same reason also when you do detect that you're being attacked, you don't want automated tools that automatically block them or black hole them or anything like that, because you will denial of service yourself. I promise you. You can have those things. If you have an entire enormous operations team and they create automated tools, I mean, that's a different thing, but if you just want to find out about it. And then you can talk to your upstream providers and try to get them help. Yes? I need to, well, if I want to watch it, I do, in order to use it for debugging purposes, I mostly use Charles actually to debug things. So not as a secure, I mean, I use it mostly not to do reverse engineering, but actually as a development tool to check network traffic. And I then have to turn things off so that I can get in there. So that's true. But I mean, I mean, the pinning does stop Charles from sniffing HTTPS traffic, absolutely. Okay. Have a great conference.